Hello, welcome to this training module, Establishing Pipe Grade, one of a series of modules related to subsurface drainage design. Our goal with this series is to provide you with the knowledge you need to design subsurface drainage systems and underground outlets. I'm Bruce Atherton, agricultural engineer with NRCS in Ankeny, Iowa. Let's get started to learn how to establish the grade for a main and a subsurface drain or underground outlet system. The capacity of a subsurface drain pipe is determined by the pipe size, material, and grade. In this presentation, we will illustrate how to establish pipe grade for a subsurface drain. Unless we have a site with uniform slopes, the final grade on the pipe will depend on several factors. We will list these factors here, then describe them in more detail in the following slides. Finally, we will illustrate the process of selecting a pipe grade with an example. The design depth and grade for drain pipe depends on several factors: the outlet elevation, the depth of low areas in the field, the elevation of connecting laterals, the need to maintain a minimum cover over the pipe, maximum burial depth restrictions on the pipe, the capability of the machine installing the pipe. We will need to know all of this information to complete a design for a subsurface drain pipe. The 606 standard provides some criteria for the subsurface drain outlet. Outlets must be adequate for quantity and quality of water to be discharged. The outlet invert must be above the elevation of normal flow and at least 1 foot above the channel bottom, where the outlet is in a channel. Existing subsurface mains utilized as outlets shall have a minimum capacity as specified in the 606 standard. We need to factor in the elevations of low areas and the distance from the main in order to provide gravity drainage. In some cases, a sump and pump are used to drain depressions where gravity flow is not practical. The elevation of the main at junctions with laterals needs to be factored in. Where we have junctions with laterals or submains, we want to bring the flow line of the laterals or submains to the main at the midpoint of the main or higher if possible. This will allow gravity flow into the drain. For example, the flow line of a 4-inch lateral pipe should be designed to enter a 12-inch main about 1/2 foot above the flow line of the 12-inch main or higher. The required cover over a pipe can be found in the practice standard or from the manufacturer. The NRCS practice standard subsurface drain 606 specifies that in mineral soils, the minimum depth of cover over subsurface drains shall be 2.4 feet. In organic soils, the minimum depth of cover after initial subsidence shall be 3 foot. There are exceptions to the standard for specific situations. The maximum burial depth for flexible conduits can be found in the underground outlet standard. Here is a table from the 620 standard that provides minimum and maximum cover requirements for typical plastic pipe used in subsurface drains and underground outlets. You can see that the maximum cover in the trench condition is between 11.2 and 20 feet. This is not an absolute condition. Certain bedding conditions or protective measures may make it possible to exceed these values, but you will have to check with your engineer. The limitations of the trencher or plow is a major factor when we decide on the depth to install a drain. The installer will know the maximum depth a machine can install pipe. However, you may not know this during the design, so you'll want to be conservative when possible. Some things to consider: older machines may have a limit of about 5.5 feet. The deeper the pipe is installed, the higher the cost, which argues for keeping the drain as shallow as possible. However, in some cases you cannot avoid deep cuts. If deep cuts cannot be avoided, special machines can be brought in, or enough soil can be removed to allow the pipe to be installed. Obviously, this will add to the cost. If you see this may happen, it would be wise to consult with the landowner and its installer to discuss the alternatives prior to completing the engineering plan. In order to complete a subsurface drain or UGO design, we will need to survey the site. LiDAR data will be useful for planning, but a site survey will usually be required to establish design elevations to the hundredths of a foot. We will need a survey of the area the drain serves, which shows elevations for the outlet, the ground surface, low areas the drain is expected to serve, the flow lines of existing drains that will be served by the new drain. As I mentioned, LiDAR data will not show the location and elevations of outlets, existing subsurface drains, and other features. Once we have the survey, we can plot a profile of the ground surface and important elevations to help us with our design. To draw the profile, we begin at the outlet, show the ground surface, and show other relevant elevations, such as laterals and low spots. And we want to extend the profile to the upper end of the alignment of the drain. The following slides will illustrate the process used to establish the grade for an example subsurface drain. Here is a plotted profile along a proposed pipe alignment. This is done in AutoCAD, but could be done by hand. Certainly it was done by hand for many years before we had computers and AutoCAD. As I mentioned before, stationing begins at the outlet and increases upstream, and this follows the route of installation. With the ground surface plotted, we want to note the high and low spots along the profile and draw in any other points that may affect the drain design, such as laterals, locations and elevations, outlet elevations, etc. We need to note the elevations that control the pipe depth on the working profile drawing. In this example, we are using the drainage district main as the outlet, so we'll add the flow line of the drainage district main to our profile. As you can see in the lower left-hand corner at station 0 plus 0, 0. Next, we want to locate our low points on the ground surface. Starting at 0 plus 0, 0, we can look at the different points, low points on the profile, or depressions. And here we've shown these on the profile. Next, we want to look at high points on the ground surface profile. And I've marked 2 here on this profile. There are no lateral connections in this example, so we don't have to show those. With the important ground surface elevations noted, we'll need to determine the pipe depth. As mentioned before, this will be constrained by both the minimum and maximum depth criteria specified in the 606 and or 620 standards, or specified by the pipe manufacturer. The 606 standard calls for 2.4 feet of cover in mineral soils. And to find the flow line, I'm going to add 0.6 of a foot for the pipe diameter, such as we might have for a 6-inch pipe. We do not want to exceed the capabilities of the machine doing the installation, and I'm going to use 6 feet depth for this example. And we're going to locate these elevations at each control point that we noted before, the high and low points on the profile ground surface. So I'm going to use red X's to show the minimum depth criteria on here, the 3 foot below the ground surface. And starting at 0, 0, we can draw these in just at the same point where we have control surfaces from the ground surface profile. Okay, next we want to look at our maximum depth, which we're using 6 feet for this example, and I'm going to use blue X's for these And we'll draw these in, starting at 0, 0. So now we have a minimum and maximum depth. We can place this tile to meet our depth constraints, and we'll have to see how that works out in this situation. So next we wanted to sketch in a line which represents the pipe flow line between these control points. Starting at the first point, we can draw in a line there, trying to keep it approximately at the midpoint. And the same thing with the next reach, and we'll just go to continue on up. Now if we get towards the upper end of this profile, we can see that we're going to have a low spot we have to keep under. So at station 7 I've kept my sketch line just above the maximum depth and kept it pretty flat going through our low area. Okay, this line has about 4 different grade breaks in here, so it might be possible to draw a line with fewer grade breaks. So let's try that, and I'm going to use a dashed line here for this. And here I'm successful in drawing one with only 3 grade breaks, and that's going to cut down on our calculations we have to do. As you gain more experience with this, this will become easier. Okay, so let's draw in our second profile, the one with the fewest grade breaks. In this example, we're going to be constrained at the upper end because of our low spot, our little depression, and then our high spot where the pipe has to go through. So we need to maintain cover in the shallow area at station 900. Yet we have to plan to be at less than the maximum depth at station 700. And I want to remind you that it's always a good thing to round off grades and elevations. I think it makes for a neater plan. So let's look at this. We need a pretty flat grade between 700 and 900. So we can estimate the grade by looking at the elevations of our minimum and maximum elevations that we found there and do the calculation. So come up with a 7/10 elevation difference, and we're 200 feet apart, and that calculates out to a 0.0035 feet per foot grade, or 0.35%. To be conservative, I'm going to use a grade of 0.1%. We don't have to go that flat, but that's what I've selected to do. So we have 200 feet times 0.001 feet per foot. That gives us a 2-foot elevation change between station 900 and station 700. I'm going to set the flow line at 1133.50 at station 900. Then at 700, the flow line elevation is 1133.5 minus our 0.20 elevation difference, giving us a value of 1133.30. And here you can see the control points and the elevations being drawn in. If we look at this, we can see that our profile line falls between our minimum and maximum elevation criterion. So we're going to say that's okay. That's a good grade and depth. So let's move on to the next reach downstream. And if we look at this by observation, we can extend the pipe at this same 1/10 grade to about station 5 plus 50. And that makes things simple. The installer won't have to change grade there. So we can calculate our elevation at 5 plus 50 is 1133.30 minus 0.15, the elevation change in that 150 feet at a 1/10% grade. And we find our elevation at 5 plus 50, our flow line elevation is 1133.15. From our sketch, the next reach and grade rate can be at station 2 plus 50. And you'll notice I'm trying to get her stationing at even hundreds or even 50 stations. Okay, we can estimate the grade here, starting at the station 5 plus 50 at 1133.15, looking at 2 plus 50, we're at about 1118.00. We've got 300 feet of distance there, and that calculates out to a grade of 0.0505 feet per foot. I think it'd be a good idea to round that up to 5% or 0.05 feet per foot. So that's what I'm going to do. So in 300 feet at 0.050 feet per foot, that gives us a 15-foot elevation change. And we can take that, subtract that 15-foot elevation change from our elevation at 5 plus 50 and get an elevation at 2 plus 50 of 1118.15. And we can see that every point, the tile profile, flowline profile falls between our control points in that reach. So this elevation will meet the depth design criteria. So we're going to call that good. Okay, next, our next reach is going to end at 0, 0. We can estimate the grade that we have between those 2 points, just like we have before, by the 4.45 difference in elevation divided by the 250-foot distance we have. Next, we want to calculate the elevation at 0 plus 0, 0 with a grade equal to 1.50%. So our elevation at 0 plus 0, 0 is going to be our elevation at 2 plus 50, 1118.15, minus the elevation change over 250 feet at a 1.5% grade, and that gives us an elevation of 1114.40 at station 0 plus 0, 0. Okay, this exceeds our 1113.70 maximum depth criterion, and it also is above our flow line criteria for the drainage district main. So we can say that's okay. So now we've completed a design profile for our proposed main. Now, given this information, now that we have grades, we can calculate the capacity of the pipes in each reach, since we know the grade. And if the final pipe size changes so that our depth criteria no longer met, we may have to adjust the grade and elevation for some of the reaches. But in this case, we've seen how to do that. We've run through 3 different reaches, and we've illustrated how to establish the grade for a subsurface drain by showing the control points and corresponding elevations on a profile, using those elevations to define a working flow line profile for a subsurface drain. And then after determining a grade for each design reach, the next step is going to be to calculate the capacity of a given pipe for each reach. So this pretty well our program. The next presentation will show us how to calculate the flow capacity of pipes. I hope you found this presentation helpful. Please call or email me if you have questions or comments about this subject. I'm always looking for ways to improve these presentations. And good luck.